Okay, so welcome to my series of videos on statistics. And in this particular video, I'm going to talk about analysis of variance. So kindly go to my channel, kindly subscribe, like, comment, and share. Now, this topic is particularly interesting because we are going to analyze a test of difference among 3 or more groups. Okay, so up until now, we've spoken about test of difference for 2 groups or 2 separate groups. That is the independent t-test. We've also spoken about the test of difference for 1 group before and after an event. That is the paired t-test. Okay. Now we can have a situation where we want to test differences in mean among 3 or more groups. And that brings us to what we call the analysis of variance. The analysis of variance. So by definition, you realize that analysis of variance, it is used in this situation. It is a common situation when someone needs to determine whether 3 or more populations have equal mean, all right? Now, the tool used to analyze such a situation is called the one-way analysis of variance, okay? So the part that is called the analysis of variance, you can shorten it and call it ANOVA. So technically, we can name it as one-way ANOVA, one-way ANOVA, one-way ANOVA. Now, when it comes to one-way ANOVA, let's look at this example. Now, how do we know the question is requiring us to do one-way analysis of variance? Now, let's assume that we have 3 separate classes, okay? So let's assume that we have 3 separate classes. So let's assume we have MBA with specialization in management. Let's assume we have MBA with specialization in marketing. Let's assume we have MBA with specialization in finance. Now let's assume that for this group, their average score in a test or in an exam, let's assume they had 82 marks. Then for this group, their average score in an exam, let's assume they had 90 marks. Then for this group, the average score in an exam, let's assume they have 76 marks. Now, if I want to test whether there is a difference in their marks, okay, somebody will be thinking that, okay, one group had 82, one group had 90, another group had 76. So I can just look at this and tell myself that the one who scored 90 is 8 points more than the one that scored 82. Now, when you talk like that, all that you are doing is that you are doing descriptive statistics. Mind you, these averages we've gotten, it might be that we picked a sample to get these averages. So let's assume that these averages are actually sample means, okay? These averages are actually sample means. Let's assume that these averages are actually sample means, okay? Let's assume that these averages are actually sample means. Now, for us to be sure that this difference between, let's say, 82 and 90, for us to be sure that that will happen in the population, we have to do test of difference, all right? So all the test of difference we've done now, it is not like we cannot use the descriptive statistics to know the test of difference. We can do that. But the idea is that we need to test hypotheses to be sure that that test of difference also applies to the population, all right? So that is the essence. Now, the null hypothesis for the one-way analysis of variance is that the population mean of, let's say, group A is equal to the population mean of group B, is equal to the population mean of group C, up until, if there are n number of groups, population mean of group N. Then, if you look at this null hypothesis, the idea is that there is no significant difference in the averages among the groups, okay? Because if the average of group A is equal to group B is equal to group C, it means that there is no significant difference among the groups. Now, one of the things you must know is that when at least even one of the group is different from another, or let's say when two groups are causing a difference, this null hypothesis will be rejected because the null hypothesis says that each group has the same mean. So if one group alone has a different mean, it will differ from other groups. So the alternative is that at least two of the groups have different means. Okay. Of course, if one of the group is causing the difference, it will be different from another group. That's why we are saying that at least two of the groups have different means. Now, in hypothesis testing for the one-way ANOVA, the test statistic table that we use is called the F test, okay? We use the F test to test for difference in mean among three or more groups, okay? But then the procedure itself, the procedure for doing this is called the one-way ANOVA, okay? One-way ANOVA. Now, how do we find the F test? All right, we can read F test from a table. So as we go along, I'm going to show you how to read an F test from a table, how to read the F test from a table, all right? And that will give us our critical F. Whenever you read F test from a table, or whenever you read the F value from a table, it is called the critical F, because the critical F is what is going to help us determine the bounds, whether to reject the hypothesis or whether not to reject the hypothesis. However, the computed F, the one you compute on your own, the one you are going to compute on your own to compare to the critical F, the formula is mean squared between divided by mean squared within. So let's note it. The formula for the computed F is mean squared between divided by mean squared within. Mean squared between divided by mean squared within, all right? So keep this in mind, and then you realize that the steps we are going to follow now is the steps to get the mean squared between and then the mean squared within. All right, so we are going to use this particular example throughout the analysis of this topic. Now, let's assume that we have about 4 groups, okay? Group 1 or sample 1, sample 2, sample 3, and then sample 4. And let's assume that these are the marks obtained by each group or each sample. Let's assume these are the marks obtained by each group or by each sample. Now, remember, if you want to test whether there's a difference in the average among these samples, the null hypothesis is that the average of sample 1 is equal to the average of sample 2, is equal to the average of sample 3, is equal to the average of sample 4. Then the alternative hypothesis is that at least the average of 2 samples are different. At least the average of 2 samples are different, okay? So that is going to be the alternative hypothesis. Now we have to go through a series of steps to get the mean squared between and then the mean squared within for us to compute our F statistics and then conclude on these hypotheses. Now, to get the mean squared between and mean squared within, first of all, we have to start with sum of squared total. So sum of squared total is equal to sigma as I runs from 1 to k, sigma as j runs from 1 to ni, and xij minus the grand mean Okay, remember this, minus the grand mean squared. Now, when you see formulas like this, don't be frightened, because in writing it as expression, it is quite simple. So here in this expression, we need what we call the grand mean, all right? This is the grand mean. We need what we call the grand mean. Now, to get the grand mean simply means find the mean of all the figures here, all right? So you add 9 plus 12 plus 8 plus 17 plus all these figures here. You add everything and divide by the number of items, okay? That is one of the ways to find the grand mean. Another simple way to find the grand mean is that you can do the means step by step, all right? So the mean, so please, this is not total, it is mean, all right? What I'm writing is not total, it is the mean, okay? So the mean for sample 1, you add all these figures, they are 9 plus 6 plus 11 plus 14 plus 14. Then you divide it by 5 because there are 5 of them. When you divide it, the mean is going to be 10.8 for the sample 1. For sample 2, the mean is going to be 12 plus 16 plus 16 plus 12 plus 9 divided by 5. So the mean is going to be 13. For sample 3, the mean is going to be 9. And then for sample 4, the mean is going to be 15.6, all right? So when we have the mean of the individual groups like this, when we find the mean of the individual group mean, we should get the grand mean. So the grand mean simply is 10.8 plus 13 plus 9 plus 15.6 divided by 4. So our grand mean is equal to 12.1, okay? Another alternative for finding the grand mean is that you could add each and every item and divide by the total number of items. But I like doing the mean of each sample or each group because we are going to be using them later, all right? So now let's look at the formula for sum of squared total. It says that subtract the grand mean from each and every item. The Xij here means that each and every item, all right? Then square it and then add it. So I'm going to do it for just a few of them. Then we'll continue the rest. I'm going to do it for just a few of them, and then we are going to continue the rest. So here, remember the first item is 9, the second item is 12, and on and on and on. So here, we are going to have sum of squared total is into bracket 9 minus, so 9 minus the grand mean. The grand mean is 12.1 squared, plus you pick the second item. So the first item is 9. You can even pick them either vertical or horizontal. It doesn't change anything, all right? So the second item probably is 12. So you're going to have 12 minus 12.1 squared, plus the third item is 8. So 8 minus 12.1 squared. So you do it. So I'm using the 3 dots here to show that you do it up until the last item, which is 13. Okay, the last item is 13. So you do it step by step till you get to 13. So you now have 13 minus 12.1 squared. All right. Now, when you do this, you are going to get the sum of squared total to be 231.8. So this is the sum of squared total, all right? Now, another thing we need in our analysis is sum of squared between. Remember, another thing we need in our analysis is sum of squared between. Now, for sum of squared between, we have sigma as I runs from 1 to k, then n1 or ni, sorry, into brackets, sample mean I minus the grand mean squared. Now, in this formula, ni is the sample size for group I. Okay, xi is the sample mean for group I. Okay, so here all that the formula is saying is that pick the sample size of a certain group into brackets, the mean of that group, minus the grand mean squared, then you sum everything. All right. So remember, these are the means. So 10.8 is the mean for group 1. 13 is the mean for group 2. 9 is the mean for group 3. And then 15.6 is the mean for group 4. Remember that. And each of them, each sample has a sample size of 5. Okay. So in our formula, sample size of each group into bracket, the mean of that group minus the grand mean. So here, the sum of squared between is going to be equal to the first group, the sample size is 5 into brackets, the sample mean is 10.8, or the mean of that group is 10.8 minus the grand mean of 12.1 squared plus 5 into brackets. So the sample size of the second group was 5. The mean of the second group was 13 minus 12.1, which is the grand mean squared. Then the third group, the sample size is 5. The mean of that group is 9 minus grand mean 12.1 squared plus the last group 2 is 5. And we have its sample mean, or the mean of that group is 15.6 minus the grand mean of 12.1 squared. All right. So when you do this, you are going to have a sum of squared between, okay, sum of squared between of 121.8. All right. Sum of squared between of 121.8. Okay. Now somebody may be wondering, what is the meaning of this sum of squared total and sum of squared between? What I want you to know is that if you look at this table here, okay, the total variation the total variation in all the figures is what we refer to as the sum of squared total. All right. But we can have variation within a certain group. So the variation in group 1 alone is called the within variation. Within. All right. But if you want to look at the variation of group 1 as compared to the total variation of group 2, as compared to the total variation of group 3, as compared to the total variation of group 4, we are now looking at the variation between the groups, right? So the sum of squared between talks about the total variation between the groups. All right, sum of squared between is the total variation between the groups. Mind you, the total variation in all the figures put together, it is caused by the variation between the groups and then the variation within the groups. So technically, sum of squared total is sum of squared between plus sum of squared within. All right. Sum of squared total is sum of squared between plus sum of squared within. Okay. Sum of squared between plus sum of squared within. Now, once we have our sum of squared between and sum of squared total, there is no need to worry ourselves on sum of squared within. All right. So always in every question, you compute the sum of squared total, and then you compute the sum of squared between. When you subtract, you get sum of squared within. So technically, sum of squared within is sum of squared total minus sum of squared between. All right. So the sum of squared total was 231.8. And then sum of squared between is 121.8. Okay. So the sum of squared within is going to be 110. Okay, it's going to be 110. So that is the sum of squared within. It's going to be 110. All right. It's going to be 110. Now, for the purpose of the F calculation, remember, I said the F statistics is mean squared between over mean squared within. So the next thing we are going to find is the mean squared between and then mean squared within. So the next thing we are going to find is mean squared between and then mean squared within. Now, mean squared between is simply sum of squared between divided by a degree of freedom of k minus 1, okay, where K is the number of groups. All right, where K is the number of groups. Okay, where K is the number of groups. Where K is the number of groups. Okay, where K is the number of groups. And then the mean squared within is sum of squared within divided by a degree of freedom of nt minus 1, where nt, okay, where nt is the total sample size. Where nt is the total sample size. So let's bear these things in mind. So now let's move on. Mean squared between is sum of squared between. So remember, sum of squared between is 121.8. So 121.8 divided by k minus 1. We are dealing with 4 groups, so 4 minus 1. So 121.8, sorry, divided by 3, we are going to get 40.6. Okay. Then for mean squared within, that's going to be sum of squared within over total sample size minus 1. So the sum of squared within was 110. The total sample size is, remember, the sample size of each group was 5. Okay. The total sample size is 20 minus, sorry, here the formula is nt minus k. Sorry about that. It's nt minus k, not nt minus 1. So this is going to be 20 minus 4. Okay. Because we have 4 groups. So we have 110 divided by 16, and that is going to give us 6.875. It's going to give us 6.875. Now we are in a comfortable place to now compute the mean squared, sorry, the F statistics. So the F statistics is mean squared between divided by mean squared within. All right. So it will be 40.6 divided by 6.875. So if you divide this, you are going to get 5.90545455. So this is the computed F. All right. Now, having gotten the computed F, our next step is to do the critical F and check whether it falls within the bounds or it falls outside the bounds. Now, let's assume that we are testing the hypothesis at 5%. So let's assume that alpha is 0.05, okay? Remember, for F statistics, we will need degree of freedom of the numerator, and we need the degree of freedom of the denominator. So here, the numerator is the mean squared between, and this is its degree of freedom, all right? So the degree of freedom of mean squared between is k minus 1, okay? Then the degree of freedom of mean squared within is nt minus k, the denominator, nt minus k. So we have nt minus k, all right? Nt minus k. Okay, so remember here we'll get 4 minus 1 is 3, and then here 20 minus 4 is 16, okay? So that is the degree of freedom. So the degree of the freedom of the numerator, because in the formula, the numerator is mean squared between. Its degree of freedom is 3, then the mean squared within its degree of freedom is 16. So remember those figures. So here, D1 is 3, D2 is 16, all right? So I'm going to show you another F table in this particular video. There are several F tables, but this particular F table is for only when we are dealing with 5% level. Okay, the other videos I showed you how to use F table when there are several levels and then there are several degrees of freedom. But here, this particular table is used for 5% level, all right? So let me show you my table. So here, we have alpha is equal to 0.05. So it's used for 5% level. So we are safe. So the degree of freedom of the numerator was 4. and then the degree of freedom of the denominator was 16, all right? Because we have, let me check, sorry. The degree of freedom of the numerator is 3, sorry, and then the degree of freedom of the denominator is 16, okay? So we have 3 here. The degree of freedom of the numerator is 3, and that of the denominator is 16. So this is where they meet. We're going to get an F statistics of 3.239, all right? So the critical F is 3.329. So the critical F is 3.329. And then the computed F, as you remember, the computed F was 5.9054. 5.9054. That was the computed F, all right? So this is going to be our decision since the computed F is greater. The computed F, remember, is 5.9055, okay? So here is 55 rounded. Is greater than the critical F of 0.05, which is actually, the F figure itself is 3.329. It will definitely fall outside the acceptance bounds. If I draw a curve, 5.905 will be greater than 3.329, which is the bounds of the acceptance, right? So therefore, we reject the null hypothesis and conclude that at least one of the groups has a different mean or a different average. All right, so this is the introductory aspect. In the next video, I'm going to teach on the Tukey Kramer procedure for multiple comparison. So please kindly like, subscribe, share, comment, but most importantly, subscribe to this channel. Thank you.